So in the last classes, we already doing some problems related to response or output. So we are continuing doing the problems. So we'll do this problem. So here a signal f of t is given as 2 pi by omega into delta of t. Minus SC of omega t by 2 is applied at the input terminals of the ideal low pass filter. Okay. So the transfer function of such a filter is given by h of j omega equal to k into g into omega of omega w of omega into e power minus j omega t naught. So find its response. So transfer function is given, input signal is given. We have to find out the response y of j omega. Okay. So the given signal is f of t, that is f of t equal to 2 pi by omega into delta of t minus st of omega t by 2, and the transfer function given is h of j omega is equal to k into g into g into w of omega and e power minus j omega t naught, where g into w of omega is nothing but gate function. So it is represented like this. Gate function is represented as its value is 1 from minus 2 to minus 1 by 2 to plus 1 by 2, and the 0 elsewhere. Okay, and the 0 elsewhere, right? Okay, so so this is the gate function, right? Let y of t is the response of the filter, then y of t equal to response y of t equal to input f of t convolved with h of t, or y of j omega is equal to, it is the frequency domain. In frequency domain it will become simple multiplication, f of j omega into h of j omega. Let it be considered as equation number 1. Okay, Fourier transform of f of t is nothing but f of j omega, that is integral minus infinity to infinity. This is f of t function into e power minus j omega t dt. So that is 2 pi by omega in delta of t into e power minus j omega t dt minus integral minus infinity to infinity sa of omega t by 2 into e power minus j omega t dt, right? But this is delta of t. This is impulse function. It exists only at t equal to 0. At t equal to 0, its value is 1. So delta of 0 is 1. And e power 0 is 1. So it is 2 pi by omega into 1 minus integral minus infinity infinity sin omega t by 2 by omega t by 2 with into e power minus j omega t dt, right? See, we know that Fourier transform of rectangular function of t by tau is nothing but sin omega tau by 2 by omega tau by 2, right? So by duality property we have Fourier transform of sin tau t into omega by tau t by 2 is equal to 2 pi into rectangular function of omega by tau. Okay, so here tau equal to omega and rectangular of x equal to gate function. Tau is omega, then it will become 2 pi into rectangular of 1. So that is rectangular of 1 is nothing but rectangular of 1 is nothing but it's a gate function. Okay, so it is gate function, that is g of x, so that it will become f of j omega equal to 2 pi by omega minus 2 pi into g of w by omega, or omega by w. Okay, so g of omega by w, which is varying from minus omega by 2 to plus omega by 2. So now using the equation 1, we have y of j omega equal to 2 pi by omega minus 2 pi g into omega by w into kg into w by w of omega into e power minus j omega t naught. So by using inverse Fourier transform formula is y of t equal 1 by 2 pi into integral minus infinity to infinity y of j omega into e power plus j omega t d omega, right? But y of j omega is this expression. So 1 by 2 pi into integral minus infinity 2 pi by omega into kg into w by omega, w of omega into e power minus j omega t naught into e power j omega t d omega minus integral minus infinity to infinity 2 pi kg w by omega into e power minus j omega t naught into uh, g of w by omega into e power j omega t d omega. But multiplying, we multiply these two functions so that it will become integral minus infinity infinity k by omega into g of w of w of omega into e power minus j omega t naught into e power j omega t d omega minus integral minus infinity to infinity kg into w of omega into g of omega by w into e power minus j omega t naught into e power minus j omega t d omega. This is equation number 2. Okay, solution of the first term of equation 2 is we have to apply time shifting property. So time shifting property here e power minus j omega t into e power j omega t t naught e power j omega t j omega, which is time shifting property, so that it will become 1 by 2 point integral minus infinity to infinity 2 pi k by omega into g into w of omega into e power minus j omega naught t naught into e power j omega d omega can be written as 2 pi k by omega into g of t minus t naught. That is nothing but time shifting property. So let it be considered as equation number 3. So solution of second term of equation 2 is also y of t equal to integral minus infinity to infinity k into g into w of omega into g of w by omega e power minus j omega t naught into e power j omega t d omega. We have three cases. In case 1, if omega equal to 1. In case 2, omega is greater than 1. In case 3, omega is less than 1. Suppose case 1. In case 1, equation number 2 becomes omega is 1. So that's why it is varying from minus 1 by 2 to plus 1 by 2. The limits of the above integral are minus 1 by 2 to plus 1 by 2. So y of t equal to integral minus 1 by 2 to plus 1 by 2 k into omega value is 1. So 1 into 1 into e power minus j omega t naught into e power j omega t d omega, or it is equal to k into integral minus 1 by 2 to 1 by 2 e power j omega t minus t naught d omega. By simply multiplying this simply after doing simple substitutions, y of t will become k into sinc of t minus t naught by 2. Okay, case 2. Coming to the case 2, for this case, the limit values ranges from minus 1 by 2 to plus 1 by 2, as shown in figure 4. So that is, see here, g of omega by w to 1 minus 1 by 2 is greater than minus 1 by 2, 1 omega by 2 is greater than 1 by 2, which is multiplied with g of omega w by omega with this function, so that the multiplication will get this diagram. So it will become this integral minus 1 by 2 to 1 by 2 k into 1 into 1 into e power minus j omega t naught into e power j omega t d omega. It is equal to same thing. So it is also sinc of t minus t naught by 2. And case 3 is the limit values ranges from minus 1 omega by 2 to omega by 2, as shown in figure 5. So here these two are multiplied. So here minus 1 in figure 2, minus 1 by 2 is greater than minus omega by 2. Here omega by 2 is less than 1 by 2. So by multiplying these two, we will get g of omega into g of omega by omega is nothing but this function, so that y of t will become integral minus omega by 2 to omega by 2 k into 1 into 1 into e power minus j omega t naught into e power j minus j omega t d omega. It is equal to k into e power j omega t minus t naught by j into t minus t naught with the limits omega by 2 to. So coming to the case 3, for this case, so here the limit values are ranging from minus omega by 2 to omega by 2. So I'm multiplying these two cases, so that we will get this one. So y of t equal to integral minus omega by 2 to plus omega by 2 k into 1 into 1 into e power minus j omega t naught into e power minus j omega t d omega. Okay, it is equal to k into integral e power j omega into t minus t naught by j into t minus t naught limits omega by 2 to minus omega by 2. Omega by 2. So by simplifying this one, we will get y of t equal k omega into sink of omega of t minus t naught by 2. Okay, this is equation number 6. Right? Thus, y of t equal to 2 pi into k by omega into g of t minus t naught minus k into sink of t minus t naught by 2 for omega is greater than or equal to 1. And okay, and it is equal to 2 pi k into omega into g by t minus k t minus t naught into k omega into sink of omega of t minus t naught for omega is greater than uh, uh, 1 from equations 3 and 6. Above one is equations 3 and 4. Okay, this is about that problem. Okay, next consider the LTE system. Next problem. Consider an LTE system with the input and output related through the relation y of t equal to integral minus infinity to infinity e power minus of t minus tau into x of tau minus 2 into d tau. What is the impulse response h of t for this system? So we have to find out the impulse response. Already response is given, y of t is given. Okay, we have to find out h of t, right? Okay, so y of t is given as integral minus infinity to infinity e power minus t minus tau into x of tau minus 2 d tau, right? This is equation number 1. Impulse response of the system h of t is defined as h of t equal to, yeah, Fourier transform delta of t. Equation number 1 became h of t is equal to integral minus infinity infinity e power minus t minus tau into delta of tau minus tau d tau. Okay, delta of t minus tau d tau. So it is e power minus t minus tau at delta equal to 2. Okay, so replace delta by tau by 2. It is e power minus t minus 2 for t is greater than 0. So it is equal to e power minus t minus t minus 2 minus of t minus 2 into u of t. So impulse response is h of t equal to e power minus of t minus 2 into u of t. Very simple one. Okay, consider next problem. Consider a stable LTA system that is characterized by the differential equation d square y of t by dt square plus 4 into d by d of d y of t by dt plus 3 into y of t is equal to d by dt of x of t plus 2 into x of t. This is the differential equation. Find its response. Sorry. For the input to x of t equal to e power minus t into u of t. E power minus t into u of t. So given differential equation is d square into d square by dt square of y of t plus u into d by dt of y of t plus 3 into y of t is equal to d by dt of x of t plus 2 into x of t. Apply Laplace transform for this expression. Laplace transform of d square by dt square of y of t plus u plus 4 into d by dt. Okay, so we are applying the Laplace transform on both sides. So Laplace transform d square by dt square of y of t plus 4 into d by dt of y of t plus 3 into y of t equal to Laplace transform d by dt of x of t plus 2 into x of t, right? So it will become, so for unit step function, it is what is the input here? X of t is given as e power minus t into u of t. So u of t equal to 1 for t is greater than 0. So uh, it is equal to 0 for t is less than 0. So Laplace transform is defined as Laplace transform of x of s equal to e integral 0 to infinity x of t into e power minus st dt. What is x of t given? X of t is given as e power minus t. Okay, it is e power minus t with the u of t. That's why limits are 0 to infinity. E power minus t into e power minus st dt. So it is equal to integral 0 to infinity e power minus of s plus 1 into t dt. Right, or it is minus 1 by s plus 1 into e power minus of s plus 1 into t with the limits infinity 0. Okay, by simply substituting these values, so that it will become x of s equal to 1 by s plus 1. Let it be considered as equation number 2. Okay, from equations 1 and 2 we get y of s equal to s plus 2 by s square plus 4s plus 3 into 1 by s plus 1. Okay. Okay, y of s equal to s plus 2 by s plus 1 into s plus 3 plus s plus 1, or we can write this as s plus 2 by s plus 1 whole square into s plus 3 using partial fractions. So a by s plus 1 plus b by s plus 1 whole square plus c by s plus 3. So after simplification, we get a value is 1 by 4, b is 1 by 2, and c is minus 1 by 4. So that y of s will become a by 1 by 4 by s plus 1 plus b 1 by 2 by s plus 1 whole square plus c is minus 1 by 4 by s plus 3. So now taking inverse Laplace transform of y of s is equal to inverse Laplace transform of the entire expression, so that it will become y of t is 1 by 4 into 1 by s plus 1 is e power minus t. So e power minus t into u of t. 1 by s plus 1 whole square is t into e power minus t. That is 1 by 2 into t into e power minus t into u of t plus s plus 3 is e power minus 3t. Okay, minus 1 by 4 into e power minus 3t into u of t. So the response of the stable LTI system is y of t, that is 1 by 4 into e power minus t plus 1 by 2 into t into e power minus t minus 1 by 4 into e power minus 3t whole into u of t. So next we will see the find the impulse response of the system shown in figure. Find the transfer function. What would be its frequency response? Sketch the response. This is the impulse response of the system. So input is this one. This is output. So it is having the capacitor C and resistor R. Okay, current I is flowing like this. Transfer function of the system is given by h of j omega from this diagram. H of j omega equal to output across the resistor, that is IR by IR plus 1 by j omega C. Okay, so I into 1 by j omega C. So taking I as common, so that it will become R by R plus 1 by j omega C. Taking LCM as j omega C, so that it will become 1 plus j omega RC by j omega C, R into j omega C by 1 plus j omega RC. Defining omega 1 is equal to 1 by RC1. Okay, so replace omega 1 by 1 by RC1, so that h of j omega equal to 1 by 1 by j omega RC plus j omega RC by j omega RC, so that it will become 1 by 1 minus j omega 1 by RC. 1 by omega RC is 1 by RC1 is omega 1. That's why it will become 1 minus j into omega 1 by omega, or mod h of j omega is 1 by square root of 1 plus omega 1 by omega whole square. The magnitude response is given by this one. So omega versus mod of h of j omega, so that it will become like this. At omega equal to omega 1, h of j omega, mod h of j omega is 1 by root 2 r minus 3 dt. Hence, omega 1 is 3 dB frequency. These are our problems related to the impulse response and output response. Okay, now we are going to see filter characteristics. Okay, filter characteristics. Filter characteristics of linear systems. Filter characteristics of linear systems. The input signal is f of t and its response is r of t. Here both the input and its response are in time domain. Why? Because it is represented by f of t and r of t. Okay, f of t and r of t. So the input signal is f of t and its response or output is r of t. Okay, f of t, r of t. Input is f of t and output is r of t. Right? Input is f of t and output is r of t. Okay, okay, right. So the spectral density function of the input signal is nothing but the Fourier transform that is represented by f of omega. This is also called as spectral density function. Spectral density function or its Fourier transform. Spectral density function or Fourier transform. So Fourier transform f of omega is defined as integral minus infinity to infinity f of t into e power minus j omega t dt. Similarly, the spectral density function of the response that is r of t is also r of omega is given by integral minus infinity to infinity r of t into e power minus j omega t dt, right? Okay, but r of t is f of t convolved with h of t, right? R of t, response r of t, or output r of t is equal to input signal f of t convolved with its impulse response h of t, where h of t is the unit impulse response. By definition of the convolution in time domain, it will become simple multiplication in transform domain, that is frequency domain. So convolution in time domain will become simple multiplication in frequency domain, that is r of omega is equal to f of omega multiplied by h of omega. Let it be considered as equation number 1. Okay, the system modifies the spectral density function of the input signal, that is f of omega is multiplied by h of omega. F of omega multiplied by h of omega. So the modification is carried out according to the transfer function h of omega. Therefore, h of omega acts as weighing function to different frequencies. Okay, it will act as weighing function to different frequencies. From the above discussion, we can say that some frequency components are boosted in strength, some are attenuated, and some frequency components remain unchanged. This is true for phase spectrum also. Thus, the system modifies the spectral density function according to its filter characteristics. Okay, according to its filter characteristics. By if it is a low pass circuit, then it passes low frequencies and attenuates high frequencies. If it is band pass filter, then it passes particular band of frequencies and the remaining frequencies are attenuated. Okay, so some frequency components are boosted in strength, some are attenuated, and some frequency components remain unchanged. Okay, remain unchanged. This is true for the phase spectrum also. So for frequency spectrum and phase spectrum, some frequency components are boosted and some are unchanged and some are attenuated. Okay, so if it is a low pass circuit, it allows only low frequencies and attenuates high frequencies. If it is a band pass filter, it allows the particular band of frequencies and remaining frequencies are attenuated. So this is about the frequency filter characteristics of the linear systems. Filter that depends upon the filter. If it is a low pass filter, if it is high pass filter, and it is bad. If it is high pass filter, it allows only high frequency components and attenuates low frequency components. If it is band reject filter, it rejects particular band of frequencies. It allows remaining frequencies. Okay, this is about the filter characteristics of linear systems. Okay, next coming to the distortionless transmission through a system. Distortionless transmission. We have to transmit the distortionless transmission. Okay, a transmission. What is meant by transmission? It is said to be distortionless. A transmission is said to be distortionless if the response of the system is exact replica of the input system. So the output is nothing but the input. the output is exactly same as that of the input, then we can say that it is a distortionless transmission, right? So the output, that is the response, is exact duplicate of the input signal, then we can say that it is a distortionless transmission. If we have a different magnitude, if you have a different magnitude, so, but shape of the waveform is same. Magnitude may be different. The important thing is the shape of the waveform and not its relative magnitude. Okay. So the thing is here. The thing is if you pass the sinusoidal signal as the input signal, we will get the same sinusoidal signal as the output signal. Then it is called distortionless transmission. Maybe it has the different magnitude of the input signal as well as the output signal. If the signal acquire any phase shift during the process of transmission, they may add up to an entirely different signal. The replica, which is produced by the distortionless transmission system, may have some time delay. Then we can say that the signal f of t is transmitted without distortion if the response is k f into t minus t naught. That is, the signal f of t is delayed by t naught units with a magnitude k times the original signal, that is represented as a response r of t equal to k into f of t minus t naught. It may be shifted, time may be shifted with some magnitude k. So, but the shape of the waveform will not be changed. Okay, so that is distortionless transmission. If Fourier transform of r of t is applying Fourier transform for the above expression, r of t equal to k into f of t minus t naught. Apply Fourier transform on both sides. So Fourier transform of r of t is equal to Fourier transform of k into f of t minus t naught, or r of omega equal to k into f of t minus t naught. This is time shifting property. Using time shifting property, we get r of omega equal to k into f of omega into e power minus j omega t naught. K into f of omega into e power minus j omega t naught. But r of omega equal to, as per the definition, the convolution in time domain will become simple multiplication in frequency domain, that is r of omega equal to f of omega and h of omega. So, but uh, here r of omega is k into f of omega into e power minus j omega t naught. So, comparing these two equations, we get r of omega is equal to k into f of omega into e power minus j omega t naught, and r of omega equal to f of omega into h of omega. So f of omega h of omega equal to k into f of omega into e power minus j omega t naught. F of omega gets cancelled. So h of omega will become k into e power minus j omega t naught. That is the transfer function. Or mod h of omega equal to k into mod of e power minus j omega t naught. Okay, so the magnitude k is constant for all frequencies, and the phase shift is proportional to frequencies. That is, theta of omega is equal to minus omega t naught. That is nothing but shifting in time by plus or minus t naught units results in phase shift to plus or minus omega t naught, but it is not allowed in distortionless transmission. Hence, for the distortionless system, the phase function must be of the form theta of omega equal to n pi minus omega t naught, where n is any real integer, where theta of omega is n pi minus omega t naught. Okay, that is about the distortionless transmission of the transmission through a system. Then we will see the bandwidth of a system. What is meant by bandwidth? By before knowing the bandwidth of the system, we have to know the frequency response of the system. So the frequency response graph is represented like this. So h of mod h of omega versus omega, the frequency response will be represented like this. So A is the maximum gain versus frequency, and A by root 2 is the 3 dB gain. Okay, that 3 dB line will cut the response at two places, omega 1 and omega 2. These two uh, these two frequencies are called, this is lower cutoff frequency and this is higher cutoff frequency. The difference of these two is nothing but bandwidth of the system. So finally, the bandwidth of the system is defined as the interval of frequencies in which the magnitude mod h of omega remains within 1 by root 2 times its value at the midband. So the magnitude mod h of omega remains within 1 by root 2 times its value at the midband. That is nothing but this value, this value. So at the 3 dB frequency, that is a by root 2 times, 3 dB line will cut the response at two places, that is omega 1 and omega 2. This area is called as the bandwidth of the system. So the difference of these two, omega 2 minus omega 1 or B minus A, is nothing but bandwidth of the system. Okay, with this I am concluding the today's class. Tomorrow we will discuss about the remaining topics. Thank you.